everybody. Today we are going to continue with the chapter 25th of waves, and we'll do the relation of a plane progressive wave and its characteristics. Plane progressive wave. A wave that travels continuously from one point to another in a medium without change in its amplitude is known as a progressive wave. If during the propagation of the wave through a medium, the particles vibrate simple harmonically about their mean position, then it is known as a harmonic progressive wave. In a harmonic progressive wave of given frequency, all the particles have same amplitude, but the phase of oscillation changes from particle to particle. Now let us derive a displacement relation for the plane progressive wave. Suppose a simple harmonic wave starts from O and travels in the positive x direction with the speed v. The time is measured from the instant when it starts from the origin O. So at the origin, the equation of the wave is A sine omega t. Now, if the particle reaches at point P on x-axis at a distance x from O, then the time taken is equal to x upon v, and we can write the relation as y is equal to A sine omega t minus kx, where k is known as the propagation constant and its value is omega v, or it is also equal to 2 pi upon lambda. Now we can write the plane progressive wave the equation in various other forms, like y is equal to a sine 2 pi by lambda vt minus x, and in terms of time period as a sine 2 pi t upon t minus x upon lambda. Study the characteristics of a progressive wave. A progressive wave always travels forward with a definite velocity. The waves are in the form of a crest or a trough, that is, it's a sine or a cosine function. Every particle executes simple harmonic motion about its mean position with the same velocity. There is a continuous change of phase from one particle to another, and it varies from 0 to 2 pi. No particle in the medium remains at rest. Twice during each vibration, the particles are momentarily at rest. There is a continuous flow of energy across every plane along the direction of propagation of the wave. All the particles have the same maximum velocity, which they attain one after the another as the wave advances. As we had discussed in the previous slide, the definition of the phase, which gives the direction and position of a particle at an instant, then for a wave which is propagating the two positions at two different positions, the phase difference can be given in terms of the difference with time and also with the position. Now, if the phase difference in terms of position is known as 2 pi by lambda into path difference, where the path difference is the difference in position of the particles at two different points. Also, in terms of time, we can give the phase difference as 2 pi by capital T, which is the time period, multiplied by the change in time. So instead of path difference, we can simply write it as 2 pi upon capital T into small t. That will be the relation. Next is the relation between the particle velocity and the wave velocity. Now we know that the wave velocity is v equal to n lambda, which remains the same for the wave when it is traveling, but the velocity of the particle keeps on changing continuously. Now for the equation y is equal to a sine omega t minus kx, the particle velocity is dy by dt. So differentiating, we get it as a omega cos omega t minus kx. Now dy by dx, the slope is equal to minus ak cos omega t minus kx. Dividing the equations 2 and 3, we get the wave velocity divided by the slope as omega upon k. Now dy by dt is the particle velocity, which we've written as vp, and omega upon k is v, which is the wave velocity. So substituting the values, we get the particle velocity is minus wave velocity multiplied by the slope of the displacement curve. This is a simple numerical which shows how to find the various terms related in the progressive wave. So I've considered a plane progressive wave whose equation is y equal to 5 sine 100 pi t minus 0.4 pi x, where y and x are given in meters and the time is in seconds. Now we have to calculate the amplitude, wavelength, frequency, and the wave velocity. Now if you see from here clearly, we can see, comparing it with the equation of a progressive wave, which is a sine omega t minus kx, we get the amplitude as 5 meters directly. Now to find the wavelength, we know the value of k, which is given to us as 0.4 pi, so which is equal to 2 pi by lambda. Solving this, we get as 5 meters. Frequency, the value of omega from the equation is 100 pi and omega is 2 pi n. Therefore, n is equal to 50 pi. The wave velocity is direct, which is n lambda. We've already calculated the value of n as 50 and lambda is 5. Substituting, we get the value of wave velocity as 250 meters per second. Another example of the numerical of a plane progressive wave, where the wave is represented as 3 sine 36t plus 0.018x plus pi by 4. Now comparing it to the standard equation a sine omega t minus kx plus phi, where phi is the phase difference or phase, whichever you want, and the positive sign is indicating that the wave is traveling along the negative x-axis. It is plus 0.018x, which indicates the wave is traveling along the negative x-axis. The rest of the values can be calculated in exactly the same manner as in the previous numerical.